Good morning and welcome to the lecture number 9 of the course Water Resource Systems, Modeling Techniques and Analysis. We have been discussing now the linear programming problems, and in the previous lecture I introduced the general form of the linear programming problem, where we would be typically writing the objective function as maximize z, which is a linear function of the decision variables x1, x2, etc., xn, subject to equality constraints. So, we will add slack variables or deduct surplus variables, etc. So, we convert a given linear programming problem into a standard linear programming problem form, standard form of the linear programming problem. Then we went on to examine the graphical solution, which in fact provides us with a motivation for the algebraic solutions. In the graphical solution, you recall that we retain the original constraints, let us say 3 x 1 plus 5 x 2 less than or equal to 12 or some such thing, and then identify first associated with each of these constraints, we identify the binding region or the edge of the feasible space corresponding to that particular constraint. Then if there is a feasible region exists, the feasible region being that particular region in which all the constraints are satisfied. So, this is a intersecting region formed by all the constraints, and because we are talking about non-negative variables x1 greater than 0, x2 greater than or equal to 0, etc., we are always looking at the solutions in the first quadrant in the graphical solution. So, the graphical method is what we introduced in the previous previous lecture. Then we also introduced the general form of the LP. Then towards the end of the lecture, I was just leading to the motivation for the simplex method. Now, the simplex method is the algebraic way of solving the linear programming problems, and it is a iterative way. Starting with a given solution, we keep on improving the solutions until no further improvement is possible in the solution. Recall that in the graphical method, this is exactly what we did. We identify a feasible region, then keep increasing z value as long as we have at least one point on the z line which is in the feasible region. That z value is a feasible value, or that solution is a feasible solution. So, we keep on increasing the z value until no further increase in the z value is possible without leaving the feasible region. That is the optimal solution. Much the same way we do in the algebraic manner. We start with the solution and then keep improving the solutions until no further improvement is possible without rendering one of the constraints to be violated. So, that is the motivation for the simplex method. What we will do now is that we will take a simple two variable problem, solve it with the graphical solution, and then see how we can relate the graphical solution with the algebraic solution and how we lead to the algebraic solution with the two variable problem. So, let us consider this problem which I introduced towards the end of the previous lecture. We take maximize z is equal to 6 x 1 plus 8 x 2 subject to 5 x 1 plus 10 x 2 less than or equal to 60, 4 x 1 plus 4 x 2 less than or equal to 40, and the non-negativity constraints x 1 greater than or equal to 0, x 2 greater than or equal to 0. So, what do we do in the graphical method of solution? First, we identify a feasible region associated with these two constraints, which means we first take 5 x 1 plus 10 x 2 equal to 60, draw a line corresponding to that. Similarly, 4 x 1 plus 4 x 2 equal to 40, draw a line corresponding to that, and because we are in the first quadrant, we will then identify feasible region formed by these two constraints along with the non-negativity conditions. So, this is what we do. 4 x 1 plus 4 x 2 is equal to 40 corresponds to this constraint. So, this line gives you the upper bound of this constraint 4 x 1 plus 4 x 2 less than or equal to 40, and we are looking to the left of this. So, this is the constraint 4 x 1 plus, this is the region given by the constraint 4 x 1 plus 4 x 2 less than or equal to 40. Similarly, 5 x 1 plus 10 x 2 equal to 60 is the bound on the constraint 5 x 1 plus 10 x 2 less than or equal to 60, and the intersecting region between the region of this constraint and this particular constraint will be this region, in which any point within the region will be a feasible solution, and therefore, this region is called as a feasible region. Okay, we will mark these points O as the origin where x 1 equal to 0, x 2 equal to 0, A. Then we will also take B where this line is intersecting, this constraint is intersecting the x 2 axis, C where these two constraints are intersecting each other, and D where this constraint or this line is intersecting the x 1 axis, and E where this constraint is intersecting the x 1 axis. So, we have 6 points now O, A, B, C, D and E. What is our objective? The objective is to obtain the maximum value of z while satisfying these two conditions, which means that we would like to be in this region or on the boundary of this region and yet maximize the value z is equal to 6 x 1 plus 8 x 2. Now, that is our objective. Let us look at all these points now. Let us say that we write the constraints in the general form, that is, we will introduce the slack variable 5 x 1 plus 10 x 2 less than or equal to 60. I convert it as 5 x 1 plus 10 x 2 plus x 3 is equal to 60, where x 3 is the slack variable. Similarly, 4 x 1 plus 4 x 2 less than or equal to 40, I write as 4 x 1 plus 4 x 2 plus x 4 is equal to 40, where x 4 is a slack variable. Remember, you need to introduce different slack variables to different constraints, and all these variables including the original x 1 and x 2 and the slack variables x 3 and x 4, they are all non-negative. So, look at what we have done now. We had original 2 constraints and 2 variables, and they were less than or equal to type of constraints. Now, we have converted them into equality constraints. So, you have 2 equations now, but we have 4 unknowns. So, we have 2 equations and 4 unknowns x 1, x 2, x 3 and x 4. These are the 4 unknowns. So, because we have more unknowns than the number of equations, that is, you have n number of variables and m number of equations. What we can do is, we can obtain solution for m number of variables, that is 2 variables, in terms of the remaining n minus m number of variables. So, in this case, we can obtain solution for 2 variables in terms of the other 4 minus 2, which is equal to 2 variables. Let us say you can obtain x 1 and x 2 in terms of x 3 and x 4. Further, what we do is, we set n minus m variables to 0 and then obtain the solution for the remaining m variables. In the example that we are talking about, you had 2 equations and 4 unknowns. So, we can set 2 variables to 0 and obtain the solution for the remaining 2. So, this is the way we progress. Because it is possible for us to solve for m variables in terms of the remaining n minus m variables, the way we progress is, we set n minus m variables to 0 and obtain solutions for the m variables. Now, a basic solution we define as a basic solution. Now, these 3 definitions are important in the simplex algorithm. So, let us go through it carefully. We set n minus m variables to 0 and obtain the solution of the remaining for the remaining m variables. Such a solution where n minus m variables are set to 0 and we obtain the solution for the remaining m variables is called as a basic solution. Then the m variables for which we obtain the solution, are called as the basic variables. So, these are the variables we have not set to 0, the remaining n minus m variables we have set to 0. So, the variables for which we are seeking a solution in terms of the remaining n minus m variables which have been set to 0 are called as the basic variables. So, the m variables whose solution is sought by setting the remaining n minus m variables to 0 are called the basic variables. The n minus m variables which have in fact been set to 0 are called as the non-basic variables. The n minus m variables which are set to 0 are called the non-basic variables. Remember, it may so happen that we may get the solution to be 0 when we solve for these m variables, we may get solutions for some of the variables to be 0, but they were not a priori set to 0 and therefore, they are not non-basic variables. So, you have the n minus m variables which are set to 0 are the non-basic variables. So, you have three concepts here. One is basic variables whose solutions you are seeking in terms of the remaining n minus m variables. The n minus m variables which have been set to 0 are called as the non-basic variables, and the solution that you so obtain for the m variables is called as a basic solution. Okay, we will revisit the example now. So, this was the example. You have 2 equations and 4 unknowns. So, what we will now do is, we will set 2 of the variables to 0 and solve for the remaining 2. What are these remaining 2? They are 4 minus 2. So, n minus m variables you are setting to 0 and you are solving for m number of variables which is 2. Now, you can solve for x, you can set x 1 and x 2 to 0, solve for x 3 and x 4. You can set x 1 and x 3 to 0, solve for x 2 and x 4 and so on. So, how many ways you can do this? There are m number of variables, n number of variables, out of which you want to choose m number of variables. So, this can be done in NCM ways, which is simply factorial n divided by factorial m into factorial n minus m. So, these are the number of ways or the number of solutions that are possible, number of basic solutions that are possible. What are the basic solutions? Basic solutions are the solutions obtained by setting n minus m variables to 0 and solving for the remaining m variables. So, NCM is the number of basic solutions that are possible. So, in this particular problem then, n is the number of variables which is 4 and m is the number of constraints or number of equations in this particular case which is 2, and therefore, you get 4 factorial divided by 2 factorial into 4 minus 2 factorial which is 6. So, 6 basic solutions are possible for this particular problem. Let us see what are the 6 basic solutions and then see how the basic solutions relate to the graph that we have just drawn. We identified O, A, B, C, D and E as the corner points of this particular space. O is the origin and then you have A as the intersecting intersection between this constraint and this axis and so on. So, these are the corner points. Let us now look at the basic solutions. As I said, we will have 6 basic solutions. Let us see which are the basic solutions. You have these two conditions, 5 x 1 plus 10 x 2 plus x 3 is equal to 60 and 4 x 1 plus 4 x 2 plus x 4 is equal to 40. These are the 2 equations that you have. What is the basic solution? The basic solution is, in this particular case, we set 2 of the variables to 0 and solve for the remaining 2. Let us say we set x 1 and x 2 is equal to 0. So, out of these 4, we keep setting 2 of the variables to 0 and solve for the remaining 2. So, x 1 equal to 0, x 2 equal to 0. What happens? X 1 is 0, x 2 is 0, therefore, x 3 will be 60 and x 4 will be 40. So, this is the solution. And look at the graph, this is the point where x 1 is equal to 0, x 2 is equal to 0. So, the point on the graph is O. Is it a feasible solution? It is a feasible solution because it is on the boundary of the feasible region. So, we will say feasible solution S, it is a feasible solution. Then we will set x 1 is equal to 0 and x 3 is equal to 0. So, I am setting x 1 is equal to 0 and x 3 is equal to 0. Therefore, x 2 I will get it as 6 and from here you get x 4 as 16. Now, x 1 is 0, x 3 is 0, which means x 1 is 0 and x 2 is 6, that will be this point. X 1 is 0 and x 2 is 6, that will be point A here. Is it feasible? Yes, it is feasible because it is on the corner point of the feasible region. Then we will set x 1 is equal to 0 and x 4 is equal to 0. So, x 1 is 0, x 4 is equal to 0. From this solution, you get x 2 is equal to 10 here and x 3 is equal to minus 40. So, x 2 is 10 and x 3 is equal to minus 40. Look at this point. This point has x 1 is equal to 0 and x 2 is equal to 10. So, this is the point here, but this is beyond the feasible region and therefore, this is not a feasible point, and in fact, x 3 is negative and therefore, it is not feasible. So, the point B on the graph corresponds to x 1 is equal to 0 and x 2 is equal to 10, but it leads to a non-feasible solution because x 3 is negative, and also as you can see here, the point B is beyond the feasible region. Like this, then we set x 1 is equal to 0, x 1 x 3 is equal to 0, x 4 is equal to 0 and solve for x 1 and x 2, 8 and 2, you get point C here. And similarly, you set x 2 is equal to 0, x 4 is equal to 0, you get x 1 is equal to 10 and x 3 is equal to 10 by solving these two equations, that corresponds to point D here. And then you set x 2 is equal to 0 and x 3 is equal to 0, you get x 1 is equal to 12 and x 4 is equal to minus 8, which corresponds to this point E here. That is point E, which is not feasible. So, these are the 6 basic solutions that you could obtain. The basic solutions are, in this particular case, the solutions obtained by setting any two of the variables to 0 and solving for the other two variables. So, these out of these 6 solutions, which are the basic solutions, you see that 4 of them are feasible solutions and 2 of them are non-feasible solutions. So, in any set of basic solutions, some solutions may be feasible, some solutions may be infeasible or not feasible. The solutions, the basic solutions which are feasible are called as basic feasible solutions. In this case, you get 4 basic feasible solutions, and the basic solutions which are not feasible are called as the non-basic feasible solutions. So, these are important points that you must remember. All the basic solutions need not be feasible, and the basic solution which is also feasible is called as a basic feasible solution, and all the corner points of the feasible region are basic feasible solutions. Why they are basic? Because you have set 2 variables to 0 to obtain this solution. In this case, you obtained it by setting x 1 equal to 0, x 2 equal to 0, and in this case you obtained by setting x 1 is equal to 0 and maybe x 3 or x 3 equal to 0. Like this, each of these corner points are basic solutions and they are also feasible solutions. So, these form the basic feasible solutions. In fact, that leads us to the way we progress in the algebraic form of solution. Starting with one basic feasible solution, we should be able to progress to next basic feasible solution, which means that from one corner of the feasible region, we should be able to move to the next corner of the feasible region, from there to the next corner, etc. Each time ensuring that there is an improvement in the objective function, and until there is no further improvement possible, or you have exhausted all the corners if you want to enumerate exhaustively, or that you attain such a point beyond which there is no further improvement in the objective function possible, and that becomes the optimal solution. So, in this case you had the option of going from 0 that is O to D or O to A, and then once you come to A, let us say you have the option of going only to C, because that is the next feasible basic feasible solution. If you came to D, you had the option of going only to C, and so on. And if C was not the optimal, then you may go from if you had come from D to C, you would go to A. So, the point is that starting with the initial basic feasible solution, we should move to the next basic feasible solution such that we achieve an improvement in the objective function value. Now, that is the whole basis for the algebraic solution, which is a simplex method of solution. Let us see how we do this. So, as you saw in this particular case, there were 2 constraints and 2 variables originally, and then it became 4 variables because we added slack variables associated with each of the constraints, each of the inequality constraints, and therefore, to convert them into equality constraints, we added slack variables. Therefore, we ended up with 4 variables, and that led to 6 basic solutions, out of which 4 were basic feasible solutions. As the size of the LP problem increases, the number of basic solutions will be increasing also. And in fact, in many practical problems, the number of basic solutions will be very large. In fact, they will run into thousands, as I mentioned. So, the basic solutions can be quite large for a practical problem. And the number of basic feasible solutions, out of these many basic solutions, the basic feasible solutions can be also very large, and therefore, it is not practicable, it is not even right to do a exhaustive enumeration. What I mean by that is that we know that the solution is on the corner. So, one easier and the straightforward way is to enumerate all the solutions here, obtain a solution at A, solution at O, A, C and D, and then look at which of these solutions is the maximum value. Now, that is a straightforward way of doing it, it is an enumeration, but enumeration becomes infeasible, enumeration becomes unwieldy in practical problems, because there are simply too many number of basic variables. And therefore, as I just mentioned, we must have a method by which we start with a particular basic feasible solution and move to the next basic feasible solution, such that when we achieve this moment, we are also achieving an improvement in the objective function value. That means, the objective function value should be continuously increasing as we are progressing from one point to another point in the basic feasible, from one basic feasible solution to another basic feasible solution. So, that is the goal. Let us see how we do this now. This is our original problem, and where we had maximized z is equal to 6 x 1 plus 8 x 2. This was the original objective function. We introduced the slack variables x 3 and x 4, because these were not there in the earlier problem and they should not influence the objective function. We write the objective function with these slack variables having a 0 coefficient. That means, irrespective of the values of the x 3 and x 4 in the final solution, your z value should not be affected. So, you write the original objective function as maximize z is equal to 6 x 1 plus 8 x 2 plus 0 x 3 plus 0 x 4, and these are the constraints. So, we must be able to sequentially generate solutions now. Start with the initial basic feasible solution and then move to the next basic feasible solution. So, let us see how we do this on this problem. The first step is to determine an initial basic feasible solution. The solution has to be basic. which means that in this particular case you will set two variables to 0 and obtain the solution for the remaining two, that is a basic solution. And such a solution must also be feasible in the sense that it should be one of the corner points. So, basic feasible solution, you choose one of the corner points. In most of the problems where you have one slack or a variable associated with each of the constraints, the easiest way to obtain an initial basic feasible solution is to set the original variables to 0. In this particular case, the original variables were x1 and x2. So, set x1 and x2 is equal to 0, which means you are essentially starting from the origin, which was point O. So, the initial basic feasible solution is obtained in most cases by setting the original variables x1, x2, etc., xn. You had the original variables x1 to xn to be 0. So, you are putting all the original decision variables n minus m variables to 0. So, in this example, we set x1 equal to 0 and x2 equal to 0. These variables which have been set to 0 will be non-basic variables, and we obtain the basic variables as x3 and x4. So, by setting x1 equal to 0, x2 is equal to 0, which become in fact the non-basic variables, we write the basis as x3 and x4. So, x3 and x4 are the variables in the basis. This is called as a basis, which constitutes a vector of basic variables. Then we use the constraints and solve for x3 and x4. So, we obtain solutions for the basic variables x3 and x4 by setting x1 and x2 to 0. So, we obtain x3 is equal to 60 and x4 is equal to 40. So, this is the solution that we get, and this corresponds to point O on the graph. So, x3 is equal to 60, x4 is equal to 40 corresponds to point O on the graph, and because we had x1 equal to 0, x2 is equal to 0, your z value will be 0. Z is this, x1 is 0, x2 is 0, x3 is 60, x4 is 40, but their coefficients are 0. Therefore, z value is 0. We are starting with the origin O here, which is the initial basic feasible solution. Okay, now, so the initial basic feasible solution is obtained by setting the original variables x1 and x2 to 0. That's how we obtain the initial basic feasible solution. Starting with this initial basic feasible solution, we should move to the next basic feasible solution. How do we do that? We need to look at this basis now. This basis has two variables, which is m number of variables. Out of these m number of variables, in the next iteration or the next step, exactly one of these, either x3 or x4, goes out, and exactly one of these x1 and x2, which are currently non-basic variables, comes in. So, there are two decisions that you need to make. One is which among these has to go out and which among these x1 and x2 has to come in to form a new basis. Let us see how we do that. So, we have to generate another basic feasible solution from the initial basic feasible solution, such that there is an improvement in the value of z. So, the way we do is, you have in the current step, you have a basis or a set of basic basic values, basic variables, that is in this particular case x3 and x4. So, one currently non-basic variable, which is either x1 or x2, must be selected to enter the current basis, and one currently basic variables should make way for this entering variable. So, we have to identify which among the currently non-basic variables enter the basis and which among the currently basic variables exits the basis, departs the basis. Now, this is what we do in this case. How do we decide which among x1 and x2 should enter the basis. You look at the objective function. Your objective function is 6 x 1 plus 8 x 2 plus 0 x 3 plus 0 x 4, and x 1 and x 2 are currently at 0 level because they are non-basic variables. Now, you want to bring in either x 1 or x 2, and the question you are asking is whether I should bring in x 1 or I should bring in x 2 such that the improvement in the value of z will be the fastest. Look at the coefficients. You have a coefficient of 6 for x 1 and a coefficient of 8 for x 2, and your objective is to increase the z value the fastest. So, which variable would you bring in? If you bring in x 1, then the rate at which it will increase is 6 times the value of x 1, whereas if you bring in x 2, the rate at which it will increase is 8 times the value of x 2, and therefore, the rate at which z increases will be higher if you bring in x 2 compared to the rate at which it increases if you bring in x 1, and therefore, you will bring in x 2 here into the basis. So, because we are looking at the maximization of the objective function, we must look for that particular variable now between x 1 and x 2, which will increase the objective function value the fastest. So, in this particular case, because x 2 has a higher coefficient, higher positive coefficient compared to the coefficient of x 1, you bring in x 2. Then we made a decision that between x 1 and x 2, x 2 will come into the basis. Now, x 3 and x 4 were in the basis. Now, out of x 3 and x 4, one has to go, either x 3 has to go or x 4 has to go to make way for this entering variable, which is x 2. Which among x 3, which between x 3 and x 4 should go out? Let us see what happens. You would like to increase the value of x 2, which is the entering variable, as much as possible, so that your z value keeps on increasing. Z value increases. As you start increasing x 2, one of the other two variables which are in the basis now, that is x 3 and x 4, they will start decreasing because of the nature of the constraints. You start increasing x 2, one of the other variables will start decreasing. In fact, both of them will start decreasing. You just look at these. The constraint was 5 x 1 plus 10 x 2 plus x 3 is equal to 60. 4 x 1 plus 4 x 2 plus x 4 is equal to 40, x 3 and x 4 are the basic variables, x 1 is still 0 and you want to increase x 2 now. You have already made a decision that x 2 is coming into the basis, therefore, you would like to increase x 2. As you start increasing x 2, because of this constraint x 3 starts coming down. As you start increasing x 2, because of this constraint x 4 starts coming down. One of these, which is either x 3 or x 4, will hit 0 earlier than the other variable. Let us see which one hits 0 first. So, from this I can write x 3 is equal to 60 minus 10 x 2 here, x 1 is still 0, remember, and from this I will write x 4 is equal to 40 minus 4 x 2. So, x 3 will be 0 when x 2 is equal to 6 because of this, and x 4 will be 0 when x 2 is 10. What does this mean? This means that as you start increasing x 2 from its current value of 0, x 2 was a non-basic variable, we are just bringing it into the basis. So, from its current value of 0, you start increasing x 2. As soon as x 2 reaches a value of 6, x 3 becomes 0. And if you further increase, then x 4 becomes 0 when x 2 reaches 10. So, x 3 becomes 0 the moment x 2 reaches 6, and therefore, no further increase in x 2 will be possible, because x 3 one of the variables has reached 0 already. Any further increase in x 2 beyond 6 will make x 3 negative, and therefore, it becomes infeasible. So, the maximum value in this particular iteration that you can increase for x 2 will be 6, and that is decided by x 3 becoming 0. So, you look at that particular variable in the current basis, which becomes 0, as the entering variable increases, which becomes 0 first, and that is the variable that has to make way for the entering variable. So, between x 3 and x 4, we realize now that as you start increasing the value of x 2, x 3 hits 0 first before x 4 hits, and therefore, x 3 has to depart and make way for the entering variable x 2. So, this is how we decide which is the entering variable, which is the departing variable now from the basis. Let me just summarize what we did. First, we start with the initial basic feasible solution, and the initial basic feasible solution, normally we start with the origin, which is original decision variables x 1, x 2, etc., x n, set it to 0. In this particular example, we set x 1 equal to 0, x 2 equal to 0. So, we are starting with the origin, that is the initial basic feasible solution, and therefore, the basis will contain all the slack variables. In this particular case, the basic solution the basis contained x 3 and x 4 as the basic variables. When we are moving to the next iteration or the next step, we have to identify which among the currently non-basic variables can be brought into the basis, such that the objective function value for a maximization problem increases the fastest, and therefore, we look at the coefficients of the currently non-basic variables in the objective function. In this particular case, you had 6 x 1 plus 8 x 2 as the objective function value, and therefore, by bringing in x 2 into the basis, you will be able to increase the z value faster than you would have done if you had brought the variable x 1, and therefore, you identify x 2 as the entering variable. And which among the remaining two variables x 3 and x 4 has to depart from the basis, that you decide based on which of these variables hits 0 first as you start increasing the entering variable x 2, value of the entering variable x 2. And in this particular case, we saw that x 3 hits 0 first, and therefore, x 3 goes out, x 2 comes in. We reformulate the basis now by taking out x 3 and write the basis as x 2 and x 4. So, earlier you had x 3 and x 4, x 3 goes out, x 2 comes in, and therefore, the new basis is x 2 and x 4. This is the basis on which we move from one iteration to another iteration, one step to another step in the simplex method. Then starting with this basis now x 2 and x 4, we obtain solutions for x 2 and x 4, etc. I would urge you to go to canonical form and Gauss-Jordan elimination method of simultaneous solutions, etc. So, we use those methods, and from one iteration to another iteration, we keep solving for the new sets of variables. In this particular case, we solve for x 2 and x 4 in a iterative manner, each time converting the problem into writing the problem in the canonical form using the Gauss-Jordan elimination method, and then keep solving for the new basic variables. This is done through a tabular method, a very elegant method and very simple way of moving from one iteration to another iteration. This is a simplex method. So, we will demonstrate this with a simple example, but the basic principle remains the same. The principle is that we start with the initial basic feasible solution and then keep on improving this solution by moving from one initial basic feasible solution to the next basic feasible solution. I repeat, by moving from one basic feasible solution to the next basic feasible solution, and in the graphical form, any corner of the feasible region forms a basic feasible solution. So, we are moving from one corner to another corner to another corner, etc., until we hit the optimal value. Now, this is done through a tabular form. We will look at how we formulate the simplex table, or simplex tableau it is called, for each of the iterations. So, let us look at this problem now. Maximize z is equal to 3 x 1 plus 5 x 2. This is a sort of problem that I solved in the previous lecture using a graphical method. So, the same problem we will consider and use the algebraic method to solve for solve this problem. You have z is equal to 3 x 1 plus 5 x 2 subject to x 1 is less than or equal to 4, 2 x 2 less than or equal to 12 and 3 x 1 plus 2 x 2 less than or equal to 18. And these are the non-negativity conditions for x 1 and x 2. The first step is to convert the LP into a standard form, and the standard form that we will be using in this lecture is that the objective function will have a maximization form. So, we write the objective function always as a maximization objective function, and all the constraints we write as equality constraints. So, we write the objective function which was z is equal to 3 x 1 plus 5 x 2. So, we write maximize z is equal to 3 x 1 plus 5 x 2, convert the constraints into equality form. So, x 1 is less than or equal to 4, I write as x 1 plus x 3 equal to 4 with x 3 as the slack variable. 2 x 2 is less than or equal to 12, I write it as 2 x 2 plus x 4 equal to 12 with x 4 as a slack variable. 3 x 1 plus 2 x 2 less than or equal to 18, I write it as 3 x 1 plus 2 x 2 plus x 5 is equal to 18 with x 5 as a slack variable. So, there are 5 variables now. Look at this x 1, x 2, x 3, x 4, x 5. There are 5 number of variables. There are 3 constraints or 3 equations. So, m is equal to 3 and n is equal to 5. So, the non-basic variables will be n minus m, which is 5 minus 3, which is 2. So, you will have 2 non-basic variables, 3 basic variables. Using these 3 equations, you will solve for 3 variables. So, we need to start with an initial basic feasible solution. As I mentioned, when you have typically one slack variable associated with each of the constraints, you set the initial variables, the original variables x 1 and x 2 to be 0. So, we start the initial basic, we obtain the initial basic feasible solution in most of the cases by setting the original variables to 0. So, x 1 equal to 0 and x 2 equal to 0, we set it, which means x 1 and x 2 are the non-basic variables which are set to 0, and then solve for x 3, x 4 and x 5. Now, this is done through a tabular form. We will just understand how we go about it. So, as I said, x 1 and x 2 are non-basic variables whose values are set to 0, and x 3, x 4 and x 5 are basic variables whose solution is sought. So, my initial basis will consist of x 3, x 4 and x 5, that forms a initial basis, and this will also lead to a basic feasible solution, because we are at the origin of the feasible region by setting x 1 equal to 0 and x 2 equal to 0. Now, this we do in a tabular form. Let us understand carefully how we do this. The objective function, which was z is equal to 3 x 1 plus 5 x 2 plus 0 x 3 0 x 4 plus 0 x 5, we also treat it as one equation with z minus 3 x 1 minus 5 x 2 minus 0 x 3 minus 0 x 4 minus 0 x 5 equal to 0. So, we write the objective function z also as another equation. So, we write it as z minus 3 x 1 minus 5 x 2 minus 0 x 3 minus 0 x 4 minus 0 x 5 equal to 0. And you have these constraints x 1 plus x 3 equal to 4, 2 x 2 plus x 4 equal to 12, 3 x 1 plus 2 x 2 plus x 5 is equal to 18. So, these set of 4 equations now, the original 3 and the objective function and the equation corresponding to the objective function, these 4 equations we write it in a tabular form. We use this convention. from textbook to textbook, from instructor to instructor, these forms may be different, but we will stick to one form as far as this course is concerned. So, we write a column basis which consists of x 3, x 4, x 5 as the basic variables, and z will always be in the basis. This is z corresponding to the z equation. This is a objective function equation. So, we write z and the other basic variables x 3, x 4 and x 5. Then we have how many rows? 4 rows, 1 corresponding to z and 3 corresponding to each of the equations. So, we write row, and for z we nomenclate as 0, row 0, and row 1 corresponding to this, row 2 corresponding to this, and row 3 corresponding to this. So, you have row 0, 1, 2 and 3. Then we write the coefficients of z in each of these rows. So, this column consists of coefficients of z in each of these rows. So, in the row 0, the coefficient of z is 1, we write 1 here. In all other rows, there is no z, and therefore, in all other rows, row number 1, row number 2 and row number 3, which correspond to this equation and this equation respectively, the coefficient of z is 0, therefore, we write 0, 0, 0. So, this column we simply wrote the coefficients of z in each of these rows 1, 0, 0, 0. Then we write all the variables x 1, x 2, x 3, x 4, x 5. So, these are the variables of the problem. Each of these columns will consist of the coefficients in that particular row of this particular variable. So, row 0, which is this row 0, has a coefficient of minus 3 for x 1. So, we write minus 3. Row 1, which is this row, for clarity I can as well write. So, this is row 1 and this is row 2 and this is row 3 and this is row 0. So, x 1 has a coefficient of minus 3 in row 0. So, we write this. X 1 has a coefficient of 1 in row 1. So, this coefficient is 1, I write that. X 1 has a coefficient of 0 in row 2. So, I write 0. X 1 has a coefficient of 3 in row 3. So, I write 3. Similarly, you look at x 2, minus 5, 0, plus 2 and plus 2. So, that is how you write x 2, the coefficients of x 2. Similarly, x 3 you look at, x 3 has a coefficient of 0, then 1, 0 and 0. Similarly, x 4 has a coefficient of 0 and in row 1 it has 0 and in row 2 it has 1 and 0. X 5 has a coefficient of 0, 0, 0 and 1. So, this is how you write the coefficients of each of the variables. Then you create another column which consists of the right hand side bi, that is for each of the rows what are the right hand side values. So, you had the row 0, the bi is 0, you just fill the right hand side values. For row 1 you had 4, for row 2 you have 12, row 3 you have 18. So, the bi corresponds to the right hand side values. So, this is how you formulate the first tableau of the simplex algorithm, simplex method. So, in the first tableau all we have done is reproduce the original problem with x 1 set to 0 and x 2 set to 0 in this particular example. And therefore, the original basis will consist of x 3, x 4 and x 5 and z will always be in the basis. So, we write the first column of basis as z, x 3, x 4 and x 5. Then we use the row numbers as 0 corresponding to the z row, 1 corresponding to the first constraint, 2 corresponding to the second constraint, 3 corresponding to the third constraint and so on. Then we write the coefficients of each of the variables including the z in each of these rows. So, that constitutes these columns. Then the BI column will consist of the right hand side values. So, you have 0, 4, 12, 18. This will consist of any simplex W at any iteration will provide us the solution. What is the solution? This is the variable and this is the value. Z is equal to 0, x 3 is equal to 4, x 4 is equal to 12, x 5 is equal to 18 is the solution, and x 1 equal to 0, x 2 equal to 0 because they are non-basic variables. Remember, any variable that is not there in the basis is a non-basic variable and therefore, its value will be 0. So, what is the solution that you are obtaining here? From this W, you obtain Z is equal to 0, x 3 is equal to 4, x 4 is equal to 12 and x 5 is equal to 18, and of course, x 1 equal to 0 and x 2 equal to 0. This is how you read the solution for in any given W. So, we started with an initial basic feasible solution, namely x 1 equal to 0, x 2 equal to 0, and therefore, you obtained x 3 is equal to 4, x 4 is equal to 12 and x 5 is equal to 18. Now, the question that we have to ask at each iteration is this the optimal solution? So, the first question we need to ask is this the optimal solution? Because we need to terminate. If we are sure that this is the optimal solution, we need to terminate. So, at every iteration, we resolve first whether the current solution is in fact the optimal solution. If it is the optimal solution, you terminate the computations. If it is not the optimal solution, then we need to ask for which among the currently non-basic variables should enter the basis. That is the first question. The next question is which among the currently basic variables should depart and make way for the entering variable. So, we ask three questions typically. Is the current solution the optimal solution? How do we resolve that question? You look at these coefficients now. You have z minus 3x1 minus 5x2 etcetera equal to 0. As long as in the 0th row, which is the z row, you have at least one coefficient which is negative, the solution is not optimal. Why? Because if you have a negative coefficient, it means that by bringing in that particular value, you will be able to increase the z value further. The current value of z is 0. By bringing in x1 or x2 which have negative values, you will be able to increase the z value further, because z will be then equal to 3x1 plus 5x2 and therefore, you can increase the z value further. So, the answer to the question whether this particular solution is optimal lies in the coefficients of z in the 0th row. If you have at least one variable with a negative coefficient, it means that the solution is not optimal, because the solution can be further improved. I repeat, the answer to the question whether the current solution is optimal lies in the coefficients of z in the 0th row. If you have at least one coefficient which is negative in this particular format of solution, if you have at least one coefficient which is negative, that means that the solution can be further improved and therefore, this solution is not optimal. And then we ask the question, okay, this solution is not optimal and we have x1 and x2 as non-basic variables, x3, x4 and x5 are the basic variables. So, exactly one of these, either x1 or x2 has to come into the basis, and exactly one of these x3, x4 or x5 has to leave the basis. So, the next question that we ask is which among the currently non-basic variables x1 and x2 should enter the basis. So, which is the entering variable is the question, and we identify the entering variable. Then we ask the question which among the currently basic variables should depart the basis to make way for the entering variable, so that we can write the new basis. So, this is what we do when we go to the next iteration. We will continue this example in the next lecture. So, essentially today in today's lecture, we are formulating the motivation for we initially started with the motivation for the simplex problem, and in the process introduced what are called as the basic solutions, and then we also identified the basic variables and the non-basic variables. Remember, you have n number of variables and m number of equations. Once you convert all the inequality constraints into equality constraints, you have m number of equations and n number of variables, including your slack variables, slack and surplus variables as the case may be. So, you set n minus m variables to 0, and these variables which are forced to take a value of 0, which have been set a priori to take a value of 0, are called as the non-basic variables. And you solve for the remaining m number of variables, and these variables for which you are seeking the solution in terms of the remaining n minus m variables which have been set to 0 are called as the basic variables. So, the m number of variables which you are solving for using the m equations are called as the basic variables, and the vector or the set of the basic variables is called as the basis. The basic variables which are also feasible are called as the basic feasible solutions. And in the simplex algorithm, we start with an initial basic feasible solution and then move to a next basic feasible solution. When we are moving from one basic feasible solution to the next basic feasible solution, exactly one among the currently non-basic variables will enter the basis, and exactly one currently basic variables will depart and make way for the entering variable. And this we do in a iterative manner in a tabular form, and I have just shown how to write the first tableau. First tableau is simply reproducing the problem. We treat the objective function also as one of the rows or one of the equations by writing z equal to let us say z is equal to 3x1 plus 5x2 was the case in our example. We write it as z minus 3x1 minus 5x2 minus all the other slack variables equal to 0. So, we also treat it as one of the rows, and along with the other equations we formulate the initial tableau. So, I have just towards the end of the lecture, I have just indicated how we write the first tableau, first simplex tableau. Starting with the first simplex tableau, we move on to the next simplex tableau if we are sure that this is not the optimal solution. And we have just seen that as long as you have at least one negative coefficient in the z row, in the 0th row, it means that the solution is not optimal, and therefore, the solution can be further improved. We will continue this discussion in the next class. Thank you for your attention.